Welcome to the Deep Dive. Today we're looking at the future of AI, specifically these multi-agent systems, or MAS. I think we're all getting familiar with the idea now. You have multiple LLMs working together on, these huge tasks.
Right, things like complex scientific reasoning or generating a massive code base. It really sounds like the ultimate goal for AI, this kind of system-level intelligence.
It does. But when you look at how most of these systems actually work, they just hit this massive wall.
A huge operational wall. They're slow, they're wildly inefficient, and honestly, they're just astronomically expensive to run.
And the research we're diving into today, from Princeton, Stanford, and the University of Illinois,
Hmm.
it really nails down the culprit. It's the communication itself.
Exactly. The old way, which the paper calls text-MAS, it uses natural language, English, as its operating system. Every single thought, every intermediate step has to be fully written out as text.
And that's where you get those super long chain of thought outputs that just burn through tokens.
A massive communication bottleneck.
It is. I mean, think about it. If you're a supercomputer, but you have to stop and write a huge text memo for every single calculation, and then hand that memo to the next supercomputer.
Who then has to read it and convert it back into math to do its job. It's just a huge waste. These AI agents are constantly talking out loud when they should just be, well, thinking together.
And that's what we're here to break down. This research introduces something called Latent MAS. It's a completely new framework for, and this is their term, pure latent collaboration.
We're moving beyond just text. We're getting into the realm of shared, high-fidelity internal thought.
And that really is the key takeaway for you. Latent MAS lets these agents get huge speed and accuracy gains because they're communicating directly with their internal brain states.
They're latent representations. They only decode text for the final answer. It's the difference between running a company on email chains versus everyone just plugging into a shared, live, working memory.
Okay, so let's get under the hood here. When we say latent collaboration, what does that actually mean? What is being passed back and forth?
It boils down to two core ideas working together. The first is they replace standard text generation with something called auto-regressive latent thoughts generation.
So instead of generating words one by one like the cat sat,
Mm.
what's it doing?
It's auto-regressively generating a stream of last-layer hidden representations.
Okay, so those dense continuous vectors.
Right.
That's essentially the AI's raw internal meaning, right?
Hmm.
Before it gets flattened into human language.
Precisely. It's a much higher fidelity signal. And the second piece is how these thoughts are shared, which is through latent working memory transfer. This happens by sharing the key value cache, or KV cache, between agents.
Right, the KV cache. That's the model's immediate memory bank where it stores calculations so it doesn't have to redo them.
That's right, it provides all the context. And what's so critical here is that latent MAS transfers the entire thing, the initial input plus all the new latent thoughts. The researchers call it lossless information preservation.
So Agent B gets a perfect copy of Agent A's working memory. No need to waste time rereading and reinterpreting a text memo. But wait, this sounds powerful, but wouldn't that just break? I mean, if Agent A generates an output vector and you just feed that to Agent B as an input, those two things aren't the same, structurally speaking.
That is the million-dollar question. It's what they call the input-output alignment problem, and it is a huge hurdle. If you just feed a generated vector back in, the internal states start to statistically drift.
The whole reasoning process just falls apart.
It falls out of distribution, yeah.
It's like trying to feed a high-res photo into an old printer that only understands text commands.
That is a perfect analogy. And their solution is actually surprisingly simple and elegant. They use a small linear alignment operator. They call it an operator.
An operator, so like a calibration tool.
Kind of. And the beautiful part is they only have to compute it once for a given model architecture. It acts as a permanent map.
Ah, so you dial it in one time, and from then on, it ensures any generated thought can be mapped back into the valid input space. It keeps the internal language consistent.
That's exactly it. And this wasn't just a theory. Just applying this one operator boosted accuracy by 2.3% to 5.3% across the board. It proved how vital it is to keep that internal space structured.
Okay, so we've got the mechanism. They share thoughts, not words, and they've solved the alignment problem. Now for the part that everyone watching their cloud compute bill cares about. The efficiency gains.
The results are genuinely disruptive. Let's start with speed. Latent MAS delivered an average of 4 to 4.3 times faster end-to-end inference speed compared to the text-based systems.
4 times faster on the same complex problems. And that's even when the text systems were using, high-end acceleration frameworks.
Right. Latent collaboration just skips the whole costly decoding step. Now let's talk tokens, because that's really where the money is.
The internal dialogue in text-MAS just burns through them.
It really does. Well, Latent MAS pretty much eliminated that. The numbers are just, well, staggering.
Go on.
It reduced total system-wide token usage by an average of 70.8%, and in some cases up to 83.7%.
An over 80% reduction in tokens. I mean, when I read that, I just thought, that changes the entire economic feasibility of building these complex agentic systems.
It takes it from prohibitively expensive to actually practical.
So we see the results, but why is it this much more efficient? Why not say 20% faster? There must be a theoretical reason.
There is, and it boils down to information density.
Okay, lay the theory on us, but, in plain English.
Well, the theoretical model shows the game is so large because these continuous, dense representations, the thoughts, they just carry so much more information than discrete tokens.
Okay.
Think of it like this. A latent thought is like an entire high-definition image file. A text token is like describing one pixel from that image in a text document.
Right. The single image file contains exponentially more information than the long sequence of text describing it.
Exactly. And for the Qwen 3 models they tested, their math showed that latent thought generation is theoretically anywhere from 235 to 471 times more efficient than text-based reasoning. That's the gap that drives the 4x real-world speedup.
That is incredible. But wait, I have a question. If you're adding more agents, and they're passing around these big chunks of internal memory, wouldn't the total system token usage still be higher than, say, a single LLM working alone?
That is a really sharp question, and the finding here is probably the most counterintuitive part of the whole paper.
Yeah.
Latent MAS actually used 15% to 60% fewer tokens than even a single agent running the same task.
How is that even possible?
It's because the collaboration distributes the reasoning load. All that rich intermediate data is passed internally, so it doesn't count as expensive decoded tokens. The agents are sharing the cost of thinking.
So only the final agent has to do the expensive part, which is decoding the short final answer.
Exactly. The whole system is just drastically leaner. And this efficiency is amazing, but, it's all for nothing if the answers are wrong. The ultimate test is still accuracy.
Absolutely. And Latent MAS doesn't just cut corners, it actually improves performance. The data showed accuracy gains of around 2.8% to 4.6% over text MAS.
And up to a 14.6% improvement over a single model. So they're not just thinking faster, they are genuinely reasoning better together.
Why, though? What makes the reasoning better?
It comes down to something they call semantic richness. When they analyzed the embeddings, they found that latent thoughts have the same core meaning as text, but with a much greater diversity and expressive capacity.
It's a richer internal dialogue. It's not forced into the box of a single word choice.
Precisely. And that fidelity makes a huge difference. There's this fantastic case study in the paper that just perfectly illustrates it, a math problem about bees leaving and returning to a hive.
Okay.
So in the text-MAS version, the first agent, the planner, it makes a tiny mistake in its text output. It misinterprets when some bees return. Because the next agents have to read that concrete written mistake, it just gets locked in.
It's like a game of broken telephone. The error is set in stone from the very first message.
And the final answer is wrong. They get 15 bees.
Right. So what happened with latent MAS?
Well, with latent MAS, the lossless transfer of the internal memory means the next agents aren't stuck with a flawed summary. They get the full context.
So the later agent could almost see the intent behind the first agent's thought, even if there was a slight flaw in it.
That's the crucial difference. The continuous nature of the collaboration allows the downstream agents to reinterpret, refine, and actually correct the upstream reasoning on the fly.
It's a resilient system, not a brittle one.
And it gets the right answer, 75 Bs.
That shift from brittle text to robust continuous thought is just massive. It was also interesting that they found a kind of sweet spot for how much latent thinking is needed.
Yes, you don't need infinite internal thought. The analysis showed performance peaked somewhere between 40 and 80 latent steps.
So that's the ideal trade-off for accuracy and efficiency. Shows that focused, concise internal reasoning is what really matters. If we zoom out, latent MAS really does feel like a paradigm shift. It solves that fundamental bottleneck of early AI agents.
We're moving from agents that have to shout their thoughts in these long, expensive memos
to agents that can share a perfectly synced, high-fidelity internal working memory.
And connecting this to the bigger picture, this research really provides a scalable general framework for the next generation of agentic systems. We're watching AI evolve beyond talking and into just, well, pure efficient thinking.
And here's the provocative thought for you to take away from this deep dive. The current latent MAS we've discussed is entirely training-free. It just changes the protocol of how existing models communicate.
So what if future research goes beyond that? What if they were to adapt advanced post-training methods like reinforcement learning to specifically optimize these latent collaboration protocols?
Could you actually train agents to get better at this internal latent communication?
Exactly. Could that unlock completely new strategies for multi-agent riveting, making the 4x speedup we see today seem, almost slow in comparison?
It certainly changes what we mean by an AI conversation.